Hi everyone, I'm Yihong Zhao. I'm from the University of Nevada, Las Vegas. Today, I'm going to give a talk about a bio-inspired hybrid light trapping structure and its fabrication for thin-film solar cells. My advisors are Dr. Hui Zhao and Shengjie Zhai. Here is the outline. At the beginning, I will show you the background and the motivation, and then we go to our proposed structure design, which is Archimedean spiral structure design. After that, I will show you the highly efficient fabrication process. Based on the well-designed structure, we surely did some numerical assessment and real-world experiments. In the end, we will have the results and conclusions. So, as we all know, the solar energy is the primary source for the lives on the Earth. But for some situations or in some places, the solar irradiance is reduced. Species living in such an environment have developed a strategy to harvest the insufficient sunlight in some ways. Here are some examples. The eye structure of mouse is sensitive to the light, and that enables the mouse can find the light easily in the dark areas. So inspired by the mouse, people duplicate its eye structure and try to find out the mechanism inside. If you look at the structures, they basically contain the parabolic nanohemispheres, which give us a gradually refractive index decrease. The bottom left is the figure we published before. The structure is inspired by the viola flowers. Combining with the graphene and PDMS, the ARC showed broadband anti-reflection properties when we have the angular incidence. The top right figure gave us macro and nano structures on black butterfly wings. The macro-scale ribs support many disordered nanoholes. The diameters for these nanoholes are different, ranging from the 215 nanometers to 385 nanometers. These suspended nanoholes give us a ring-shaped fast Fourier transform, and that combines the efficient light coupling and the light trapping properties together with a high angular robustness. So, in our project, inspired by sunflowers, we have a chance to utilize their structures to further improve our devices. There are many studies on the sunflowers. For example, people found the golden ratio in their seed arrangement, and is related to the Fibonacci sequence. If we use one of the Fibonacci number and divide this number by the one before this number, the ratio is close to the golden ratio. So the Fibonacci sequence are also called as the golden ratio sequence. However, to perfectly duplicate its structure is really hard. So we first duplicate the whole structure and marked them as dots. These dots are arranged by a golden spiral. And then we simplify these dots. Finally, we found that the position of these dots were actually spread out by a single spiral. So we can conclude that the spiral can give us the benefits as follows. It can help the plants to have sufficient sunlight during the plant growth. During the plant growth, it offers the least material utilization and the lowest energy consumption. Other studies also show that the structure of the sunflower also has a good structural tolerance. The most important, it can improve the light capture capability, which is good for the solar devices. But like what I mentioned before, it is hard for us to build up a nanospiral arrangement in reality. Luckily, we found that the nanostructure formed inside an optical disc are followed by a spiral track from inside to outside, and this track is technically called Archimedean spiral. This spiral is actually what we want. It provides us an efficient way to fabricate the spiral-shaped nanostructure, and what's more, the writable disk is used to record the binary data and the digital information we want to burn into. And this function actually gives us a chance to bridge the Fibonacci number we found in the sunflower and the nanostructure we designed. The figure D you can see there is actually the SEM image in the recording layer, and we also call this kind of nanostructure as the pitch length form. It actually gives us an idea. We can program our well-designed sequence, and we can transfer this sequence to binary sequence. After we transfer this sequence to the binary sequence, we can burn this binary sequence into a disk. Meanwhile, the new formed sequence followed by an Archimedean spiral. So, because we found the Fibonacci number in the sunflower, so we choose Fibonacci sequence. The Fibonacci sequence begins with the Sj equals 1. According to the concatenation rule, the first 6 generations of the sequence go like this. To be noticed, the sequence is an infinity sequence, and it can help us to extend the pattern size no matter how big it is. Also, programming the binary data will enable us to get the exact patterns we want to get. So in this project, because we use the Fibonacci sequence, so the pattern formed by the Fibonacci sequence is called Fibonacci pattern. And it is important for us to determine the nanostructure size. We call that the nanostructure features, or the geometric parameters. For the pitch length form, we can determine the pitch size, the depth, and the track pitch. Using different disks such as CDs, DVDs, and Blu-ray will give us the different sizes of the nanostructure. And here is a table you can see there. The Blu-ray is around 150 pitch size, nanometers pitch size, and the DVD is around 440 nanometers. So we can determine our nanostructure features by using different disks. To find out the optimal disk for the light trapping capability, we did the reflectance simulation, and here is the figure. In this figure, the patterns are same, which are the Fibonacci patterns, but the pit size, the pit height, and the track gap, they are different due to the different disks we used. Comparing to other disks, the Blu-ray gave us the highest improvement on the reflectance decrease, so we choose Blu-ray disks as our mode to fabricate our coatings in this project. To be noticed, the disks only determined the nanostructure features, such as the pit size, the pit height, but the locations of the pits and the lengths are determined by what binary data we burn into. For example, in this project, we use a Fibonacci sequence, so the pattern will be the Fibonacci pattern. But if we use another sequence, such as routine sample sequence, the pattern would be the routine sample pattern. Here is a figure to show how the binary Fibonacci sequence burned into a disk, and you can see the right side figures show the nanostructures taken by the SEM, and also our simulated figures. And you can see that the fast Fourier transform shows no big difference between SEM image and our simulated Fibonacci pattern. Also, we did the power spectral density function to show our pattern having a spectral broadband power density. And here is the figure you can see there. So once we determine the pattern, the rest is to transform our pattern to real world. Remember, we have already burned the pattern into a disk. Then we can peel off the protective layer of the disk, and the nanostructures are actually located in the recording layer. We can use this recording layer as our mold to fabricate anti-reflective coating. Because our proposed ARC is arranged by a spiral, and the pitch length form are followed by Fibonacci sequence, so we call our coating as HLTSC, as shown on the right figure. To fabricate the HLTSC, we use the PDMS solution. The procedures are like this, and the red figures actually is the demo of our HLTSC on the commercial silicon solar cells. Of course, we did some experiments to test our coating. Before that, we did a numerical assessment. Remember, our pattern is designed based on the Fibonacci sequence, and its arrangement followed by an Archimedean spiral. So we want to test how the Fibonacci sequence and the spiral affect the light trapping capability. So except for our HLTSC, we also made the coating including the Archimedean spiral only, which is just the spiral, without cutting off the spiral by the binary data. It is easy to make one. We basically do not burn any data inside the disk, and the recording layer in an empty disk is a perfect mode for us. And you can see the significant reflection improvement. Is not a improvement. A significant anti-reflection decrease happened at the 550 nanometers and the 800 nanometers. When we burn the binary Fibonacci sequence inside, we improve the surface randomness, and the surface randomness broke the mirror symmetry at the microscopic and also prolonged the light path due to the multiple internal reflections. And here are the figures to show IIC, which is the short circuit current improvement, which gives us a highest enhancement around 8.6%. And here are two key factors for IIC improvement. The one is the refractive index gradually decreased, and another one is the mere scattering happened there. This is the figure to show the omnidirectional test. Under the angular incidence, our HLTSC showed the excellent angle and polarization tolerance there. And also the obvious increase the IIC within an incident angle range from the minus 70 degree to 70 degree. It surely proved that our HLTSC having a broadband omnidirectional light trapping capability. So we finally draw the conclusion. A highly efficient HLTSC is proposed based on the merit characteristics of both Archimedean spiral and Fibonacci sequence arrangement. The FDTD simulation and the optical experiments are conducted to verify the concept. And a cost-efficient manufacturing method is also provided for HLTSC. The results give us the improved efficiency on solar devices and showed us an excellent surface anti-reflection property. And I think that's it. Thank you for your attention and questions.